So far, when we've been looking at controllers, we've really looked only at two different ones. One was the open loop controller with a constant gain, and the other was a closed loop controller with a constant gain. We're going to pretty much abandon the open loop control idea because we've seen that the closed loop control has a lot of advantages, and we're going to focus on feedback controllers. This is the picture that we'll use. The general control setup is that I have the reference input on the left and I have the output of the system on the right. I measure the output, I compare it to the reference, and then I have an error signal coming into the controller. The controller D of S could be anything that I design, and I need to design that, but somehow it's a linear time invariant system that operates on the input signal, which is the error, and it produces an output signal, which is the actuator control effort, and that goes into the plant, and the plant again produces the output Y. And there's a disturbance that we also have to keep in mind at all times. We need to design a controller D of S. That's a major focus of this course. And we're going to find that there are a number of options that we could use, and one of them is called PID control, or proportional integral derivative control design. It turns out to be extremely popular. There's one paper I read that estimates that more than 90% of all fielded controllers in applications and products are PID controllers or close variants of those. Now, please keep in mind that that doesn't mean that they're fantastic, it's just that they're popular, and I guess by extension that in most applications, at least 90% of applications, PID controllers work just fine. So when I tell you that we've got 9 different controls courses at this university, this one is good enough for 90% of all fielded controllers, and the other courses are focused on the other 10%. We've looked at proportional control, and that's the P in proportional integral derivative. And now we can begin to explain why that's the case. We said in our control design, our feedback design, let the control signal, the input to the plant, be proportional, be a constant times the error. And if we do Laplace transforms of this, this gives us U of S equals Kp times E of S. And then I can say U of S over E of S equals Kp, but that's what D is. Here notice that U of S equals D of S times E of S. So D of S, by definition, then, is U of S over E of S. And so for a proportional controller, D of S is simply a constant gain, a gain of Kp, where P stands for proportional. This section that we're looking at right now is going to look a little more deeply at what proportional control can do in our motor design. And then in later sections, we're going to look at what adding integral control and derivative control can do. But here I at least mention some of the pros and cons of these different types of controller. Proportional control tends to increase the speed of response. So rise time tends to be more fast than it was before, but it can also allow non-zero steady state error to persist if it was there to be with open loop control. It can result in a large transient overshoot, as we saw at the end of the last section, and it might not eliminate a constant disturbance. So there are some limitations. It's a simple design, simple because I could even do it by trial and error. It's just one number. I can just keep trying different numbers until it works. So it can improve things, but it also can't improve everything always that we would like. I can add another term to my controller. I can say let my controller instead be some constant divided by s. And remember that 1 over s is an integrator. So the output of my controller integrates the error. And we'll look at this next section, but the big benefit of doing this is that we can eliminate steady-state errors that proportional control is not able to eliminate. But at the same time, I'm solving one problem and possibly causing another one. I could cause transient response to get worse, and I could cause the system to be less stable or even unstable when it was stable before. So I have to be very careful when adding integral control to a system. Derivative control says that my compensator is equal to some constant times s. And remember that when I multiply by s in the Laplace domain, that's a derivative. So if I take the derivative of the error signal, a derivative is anticipatory. It kind of anticipates what's happening based on the slope of the input signal. And because of that, it can reduce oscillations in the dynamic response. But it can also, at the same time, make steady-state error get worse. So ideally, we need to learn how to combine the best parts of all three of these together to make a single controller that improves steady-state error, improves transient response, and reduces oscillations. And that's why we use a proportional term and an integral term and a derivative term, or we have the entire PID controller terms. So in later sections, we're going to look at each of these controllers separately and how to use them together. And the first one that we look at is the proportional controller that we've done over and over and over again, but we're going to look at it in a slightly different way, and that's going to help give quite a bit of insight, I think. So proportional controllers compute the control effort U of t such that U of t is equal to a constant times the reference input minus the measured output, or a constant times the error. And again, as we've said, that means that d of s is simply the constant kp. And the idea behind this is pretty intuitive. So if we have a plant with a positive gain, and most do, if it has negative gain, just multiply everything by -1 and then it has a positive gain. Then if the error is positive, that means that my y is not as big as it should be, and the intuitive thing is I'm not trying hard enough. I need to try harder. I need to push harder to get y closer to r. So if I multiply this positive error by a positive gain to compute my control effort, I'm in fact trying harder. But if my error is less than 0, that means that y is too big. I've tried too hard already. So if we multiply this negative error by a positive gain, I will get a negative control effort that tries to pull the response back. So that's pretty intuitive. For most things that we control manually, we have some kind of approach like that. If the output isn't as high as I want, I push harder, and if it's higher than I want, I push less hard, or I pull back. So we return to the closed-loop poles, looking at those for the DC motor using a proportional controller, just like before. This is not new. This is from previous sections. And this is the closed-loop transfer function of the output of the system divided by the reference input. That's the complete response. And we notice that I've eliminated disturbance here for simplicity. We're simply looking at the response due to the reference input R. And the poles are the roots of that denominator equation. And remember, the poles are critical because they tell us, is the system fast or slow, is it oscillatory, and all of that that we learned about in the previous chapter. So the poles are the roots of tau 1 s plus 1 times tau 2 s plus 1, all plus 1 a times kp. If I don't have feedback, we can think of that in the limit as something like kp going to 0, because that's the transfer function we had without feedback. We had that denominator. So I had poles at minus 1 over tau 1 and minus 1 over tau 2. When I do have feedback, I need to expand that denominator to be able to find the different polynomial terms in order to find where the roots are. And so this just gets copied down there. And then we multiply out the denominator. And you'll notice just doing FOIL on this, I'll get tau 1, tau 2 s squared, plus tau 1 plus tau 2 times s plus 1, and then adding plus a times kp, and that is exactly what we have there. I put that into the quadratic equation, which says if this is lowercase a, b, and c, the roots are at minus b plus or minus square root of b squared minus 4ac all over 2a. And we'll see if that's what I have. So the first term is minus b. B is tau 1 plus tau 2. That's what I have. Plus or minus b squared. There's b again. Minus 4 times a, tau 1, tau 2, times c, 1 plus a kp, all divided by 2 times a. So sure enough, all we've done is use the quadratic formula, which is something I'm sure all of you have committed to memory at some point. It's one of those important things. And if I give you values of tau 1 and tau 2 and a and kp, you can solve that equation and find out where the roots are. Well, if all these terms are positive, tau 1 and tau 2 and a and kp are positive, it's actually possible to plot generically where the roots are going to be for different values of k in what we're calling a root locus plot. And this is something we're going to study later on in the course. I think in chapters 6 and 7, we're going to study this very extensively. It's going to be very important for us. So this is a preview of what one of these plots looks like. But the idea is these roots change when k changes. Those root locations are a function of k. And we just said when k is equal to 0, that's essentially open loop control, so those values are going to be at minus 1 over tau 1 and minus 1 over tau 2. But for any other value of k, I'm going to have different closed loop root locations than what I started with. And here is our very first root locus plot in this course. And so let me take a minute to explain what this is trying to show. So this is an S-plane, and so this is imaginary part of S on the vertical axis and the real part of S on the horizontal axis. And what we would like to know is where are the closed loop roots of my controlled system when I use a proportional controller. And we said when kp equals 0, I've got a root there at minus 1 over tau 2, and I've got another root there at minus 1 over tau 1. If I have kp that is bigger than 0, think of kp as some kind of an adjustable slider or a knob, and I started in the 0 position, but then I move it away from 0, and as I do that, and I solve that quadratic equation, this pole moves to a different location to the right, and this pole moves to a different location to its left. And so for a small positive value of kp, I would have poles there and there instead of at minus 1 over tau 2 and minus 1 over tau 1. Well, let's think about what that means. Remember we said that the origin is our reference point when we're thinking about the dynamics of a system. The pole that is closest to the origin is the dominant pole in the response. So I started out with two real poles, and we go back to our picture. What does a real pole response look like? Well, a step response looks nice and smooth. And one of these is going to be fast, this one, and one of them is going to be slow, this one. And so the slow one dominates. So I started out with a pole at -1 over tau 1, so that's a very slow response. And as I increase Kp, that pole moves farther away from the origin, and so its transient, its rise time gets faster, its settling time gets faster. The rise time gets faster because the semicircle of this has to get bigger to be that one, so omega n is bigger. Settling time is faster because the sigma value, the real part, goes further out. And the overshoot, there is none because it's still on the real axis. So by increasing K, I've improved performance in every way imaginable by increasing it a little bit. If I increase K a little bit more, I move the pole farther, and it'll move out here. Those two poles will start moving close to each other. It'll move there. And that's going to make my response even faster. My dominant pole, still closest to the origin, is going to be farther away from the origin, and so it's going to be faster, and I'll get better response from this system. At a critical point, and that critical point happens, and you can verify this in the quadratic equation, when Kp is equal to tau 1 minus tau 2 squared over 4 tau 1 tau 2 times A, the two poles end up right on top of each other, right there. And I've got two real poles at exactly the same location. And they're still real poles, so there's still no overshoot. The omega n is larger than it was before, so my rise time is faster, and the sigma is farther away from the origin than before, so my settling time is faster also. Great. Now something interesting happens to these roots. And if you look at the quadratic equation, it's obvious. It may not be obvious otherwise, but here what happens is if I make K large enough, then that term is bigger than the tau 1 plus tau 2 squared, and the thing inside of the square root becomes negative. And when I take a square root of a negative number, I get an imaginary number. So I have real plus or minus imaginary divided by real. That's a complex set of conjugate numbers. So if I turn up the gain enough, this pole has moved to some point up here, and this pole has moved to some point right down there. And the response that we get from that is a little bit mixed. The omega n is, again, this distance from the origin here, so that's a little bit larger than when the poles were right at that junction point. So my rise time is going to be a little bit faster than it was before. The settling time has not improved at all because my sigma is exactly the same as it was at that junction point. And now I start getting oscillations and overshoot because if we look at this angle here, this angle is not equal to 90 degrees, and so the inverse sine of that angle is going to give us some zeta factor that's not equal to 1, and we'll start to oscillate. And so the step response in this regime is going to look something like this. It's going to be faster, the rise time is faster, but everything else is really no better. And the oscillations make it probably less desirable. So that's what a root locus plot does. It plots the path of roots as I change the gain of the system. So this root started at its open loop location, and it moved that way and up that way, and as I increased that gain, and this root moved that way and that way as I increased the gain of the compensator, Kp. And so our job as control engineers, if we use a proportional controller, would be to choose the value of Kp that we think best meets the specifications. And so it may be the value of Kp that puts the poles right there, or maybe we can tolerate a little bit of overshoot to get a faster rise time, and it might put the poles there. Or maybe we really don't want to push that hard. The control effort is a concern, so we put poles right there. But the root locus plot helps us to understand some of those trade-offs a little bit better. So I think we've said this already, but I'll just summarize. If I have a value of Kp such that the poles are still on the real axis, the poles are moving horizontally toward each other, the rise time gets faster because the dominant pole is moving farther away from the origin, and omega n is increasing. Settling time gets faster since the real part moves farther from the origin, so the size of sigma is bigger. The damping remains the same because there was no overshoot to begin with. There's still no overshoot. Once the poles hit that, the gain hits that critical point and the poles split apart, they become complex conjugates. They gain some imaginary part. After that point, the settling time stays the same since the real part of the pole location is unchanged. The rise time gets lower because the natural frequency omega n is getting bigger. The poles are getting radially farther from the origin, and the overshoot increases though since the damping decreases. In this example, I could crank up the gain Kp to be as large as I liked, and you notice this here, that this just keeps on going, straight up and straight down. And it never curves over to the across the imaginary axis to go into the right half of the S-plane where the poles had become unstable. So I can have even infinite gain in this system and it would still be a stable system, but it becomes more and more and more oscillatory, and that's not desirable. It turns out that if we have any more complicated example than this one, it's very possible that if I have systems with more poles than this one, that increasing the gain of the system will lead to instability. So how do we improve our tracking and our accuracy but keep stability? Can't always do that with a proportional controller. Sometimes I got to work harder. So the next section looks at integral controllers.